Okay, so in this problem we have a particle which weighs 10 pounds and it's released from rest and slides down a smooth curved rod and sticks to block A, which itself has a given weight. Based on this information, we're asked to determine the maximum deflection of the spring attached to A if the spring has a given value of stiffness. Okay, so I think the key thing to note here is that we're looking at a problem that's going to have to be broken into multiple parts. The reason for this is it's very nice to use work energy to account for the change in speeds due to this change in height. But because we have an impact event going on right here, I can't use energy throughout the problem. So what I'm going to try to do is I'm going to try to break this problem into two parts. I'll start here at position 1, move to a position 2, which is immediately before impact, and then identify a state 3, which is actually some later instant in time, which is post-impact. In particular, I'm going to try to use the linear impulse momentum method to move from 2 to 3, and the work energy method to go from 1 to 2. So in this regard, let me go ahead and start by looking at this problem over the interval from 1 to 2. And if I do that and draw, say, a free body diagram of my particle P, I know I'll have some normal force acting from the track and the weight. I know by definition normal is always going to not do any work here, and that the weight's accounted for in the potential energy. And so I can go ahead and solve this problem using the work energy quite easily. So in this regard, what I would say is that T1 plus V1 plus U1 to 2 non-conservative is equal to T2 plus V2. Now if we go up to the problem statement here, we can note that the particle is initially released from rest, I believe. Indeed it is. So if I do some substitution, I'm going to have my first term here as 0. I'm going to add to that the initial potential energy. Let's go ahead and call this bottom level here to be the datum. So if I do that, the second term here is going to be plus the weight of the particle, which I'll call WP, times H, where I'm going to go ahead and define H to be this given value. I'm going to have no non-conservative work contribution, so the second term will be 0. And that's going to equal T2, which is going to be 1/2 times the mass of the particle, which is WP divided by G, times its speed at state 2 squared. And V2, because we haven't yet started to compress the spring, will simply be equal to 0. So I can use this and find, for example, that V2 is going to equal, if we do a little bit of math here, we're going to have 2G times WP times H divided by WP. WP's will cancel, so and this is under a square root, of course, so I'll have this is equal to the square root of 2 times G times H. Now that gives me the speed. If I have that now, I can go through the impact event. And I'm going to go through the impact event assuming that the spring's not actually compressed during that. So I'm going to assume the spring has no effect. And so if I go through 2 to 3, what I can say here is that I'm going to assume linear impulse momentum in the x direction is conserved. Again, noting that the spring's not compressed. So in this regard, what I can say is that pre-impact, well, I should draw a free body diagram here, of course. If we draw the system now to be P and A, I'll have the net weight of the system acting down. I'll just call this W. And I'll have a normal force, acting up from the rod, so I'll call this N. And so there's nothing in the x direction. So what this is going to give me is that the mass of the particle, so WP divided by G, times V2, is going to equal the weight of the total system, which sticks together, which is going to be WP plus WA over G times what we'll call V3. So in this regard, I can find V3, namely V3 is going to equal, well again, we can look up here, the G's are going to cancel out, and so I'll have V3 is equal to WP divided by WP plus WA times V2. Now initially I said I was going to break this problem up into 2 steps. I actually need to break it up into 3 because now all we found is the post-impact velocity of this total system. But what I really am asked to find in the problem is actually the maximum deflection of the spring. So I'm now going to define an intermediate state, which is a compressed state here, and I'll call this state 4. And that's where we can get this maximum compression. Now because we're essentially have a speed and we want to just find max compression, I'm going to use work energy from instance 3 to 4. And so if I do this now, I'll have that T3 plus V3 plus U3 to 4 non-conservative will equal T4 plus V4. If I draw a free body diagram of the system here, here's our two particles stuck together. We'll still have a normal force acting up, we'll have a total weight acting down, and now we'll have some spring force acting here. We know the weight and normal force are not going to contribute in this case because they're going to balance each other out, and so the spring force is all I need to be worried about, and that of course will appear in my potential energy. So what I'll have here is 1/2 times the weight of the total system, which is WP plus WA divided by G, times V3 quantity squared, is plus, initially I have 0 potential energy, plus, I have no conservative work, is going to equal, at point of maximum compression, we'll have 0 kinetic energy, plus 1/2 times K times the amount of compression delta squared. I can take this equation now and solve for the value delta. Now if you'll note, delta is dependent on V3. Let's call this equation 1. We can get V3 from here, which we'll call equation 2, in terms of V2, which we can get from here, which I'll call equation 3. So if you solve these 3 equations, 3 unknowns, you can have the answer to your problem. Okay, from here on out, it's just basically an exercise in substitution. I'll leave that up to you to do. Best of luck, everyone. Take care.